Romans had ever done. A lot of things Romans had done. Congestion pricing was done by Romans, I'm told, because they had too many horses in the city center, and I believe they were actually doing time, scheduling and all those kind of things. But I don't believe they ever had a traffic signal in the Romans' time. Now, my friends always tell me that I say that everything was always invented in India before everything. But I don't think that traffic signals are mentioned in any Indian Puranas or old books or anything. So as far as we know, it came first in London, and it was outside the House of Parliament, and it was a semaphore system, and understandably so, because trains were already sort of there, and they had developed a semaphore system, which, I don't know if any of you students have seen, train signals with an actual mechanical arm and all of that. That's basically what they had in London for it. And if you can probably see in the picture at the top of it, they actually had lights, green and red lights, but those lights were running on gas. They were not electric lights. And as it turned out, at one time it caused some big fire, and the policeman that was guarding it below it got severely injured, all kinds of issues. So it didn't really become the standard. And the real first electric signals were designed in the US. It was developed by Lester Wire and installed at Cleveland, Ohio. And there are very interesting stories on the bottom two pictures, which are the first electric signals at Cleveland, Ohio in 1920 or 12 or something like that. It's much before the MUTCD. You can actually see that above the signal, there was a little cage kind of a thing, and somebody could sit in there, I believe. And so people used to call it bird cage. And they used to call it Wire's cage. Lester Wire, who designed it instead of cage of wires. Anyway, and then people used to apparently make fun of the whole thing. They'll stop out there like, any birds coming out? I didn't see any bird, so can I go? All these kind of things. So that's old history of traffic lights. So, we have a long history of more than a century, and at least 90 years or more than 100 years of traffic signal lights itself. As you can see, MUTCD, which still exists as MUTCD, Manual on Uniform Traffic Control Devices, sort of the Bible of traffic designs in the US and all of that. MUTCD still exists, and it is updated. Moving on, just one more police notice. By the signal caution, all persons in charge of vehicles and horses are warned to pass over the crossing with care and due regard to the safety of foot passengers. Signal stop will only be displayed when it's necessary that vehicles and horses shall be actually stopped on each side of the crossing, blah, blah, blah. So, that's the original announcement on their signal control. Okay, that's just to prime the topic. So what is traffic control that we have always been doing? I'm going to just go over the basics of this itself, and it's all in just words, okay? So what happens at a traffic signal? We do not allow traffic streams that have any crossing conflicts, two of them to move at the same time, and that's for safety reasons. And this was always the basic reason for signal control and red lights and green lights, that if there would be a conflicting movement, then we will actually give it a red signal. So two streams are allowed at a time, two through movements it can be. It could be a through movement and a left turn, it could be. Or it could be two left turns. It's all possible. And if you actually consider, this is left turns in the US, not in the, not in UK. So some streams of merging flows are allowed too, not all, from right turns. So unless otherwise specified, and that is for congestion reasons. I mean, we normally allow a right turn to happen at any time, whether it's red or green, because the assumption is that the right turning traffic can always merge to the through traffic that it's merging into, and that's not a problem. There won't be a conflict. Except sometimes it is prohibited for efficiency reasons. It's prohibited, I said, for safety, for congestion reasons. It can also be said as efficiency reasons. So how safe are merging or car following movements in comparison to crossing movements? Have any of you thought of, I mean, why are we so worried about crossing movements? And we don't think about accidents when we are following each other. I would make a one second. I would make the argument that at first, when people started driving cars, just following each other was also a pretty stressful part of driving. You didn't want to go and hit somebody. You need to be constantly watching out. And it's all the whole driving. You are driving behind somebody and you need to keep on watching out for accidents, and you don't run into accidents. So why do we worry so much about crossing cars? Okay. I'm just gonna, yeah, go ahead. Yes, that is, rear end is much less severe. Agree. So, I mean, if we can avoid serious collisions, we don't have to be that afraid. I mean, we have collision warning systems now, So maybe we should just pull back on our fear of crossing movements. This is the premise of some of what I'm talking about today. So traffic control, class notes from Professor Jin is going to come now. So what happens when we stop a stream with a red signal and we get a queue? And this is known, it's taught to undergraduate students everywhere, probably taught better than anybody by my dear colleague, Professor Jin. So I'll show his notes. This is from several years ago. I mean, this is not this current notes. At some point, I didn't want to type this stuff. So I thought, well, Long had written this, so I'll use it. So, but what I wanted to point out was the blue area that most of you here who have done Professor Jin's course will know very well about, and some of you may not have thought about. It's basically showing an arrival flow over time, accumulated flow of vehicles that are arriving, which is that straight line at an angle that you see out there. And then what happens is that the departure flow ends up getting stopped at over a period of time, and then they start moving again at typically saturation flow rate after that. So this period during the red period that you see out there, they are stopped. There is no departure flow, and the arrival flow is still happening at that steady rate. And then the question is, what is the total delay that you get out of it? So there was a famous delay curve that you would have all heard of by Webster, the famous Webster's delay function that came from England, and in the 50s, 60s. And the first two terms of it are easy to solve mathematically. You can find it mathematically. First term is especially easy to do. And in fact, I think Professor Jin has just written it out there because he just quickly calculated it. So, I mean, you don't need a derivation for really the first term, and which is just the area of the blue, the blue area that Professor Jin shows. That is the first term, and that is the primary delay, Q delay. the largest fraction of it. But then what that is under the assumption that you have like a steady flow of traffic. And in reality, that may not be there. It could be a random case. And Webster went ahead and assumed that the randomness is the worst randomness, which is like Poisson random, which is the worst randomness, right? He assumed Poisson and added a second term, and then figured out, nah, the real world is not Poisson. It's something, something better than Poisson. It's not that random. So a third term was added, which is like an empirical adjustment factor. So this is kind of known. The only thing that I wanted you to just kind of look at it. This is all for you to just think in your mind about what intersections do. And the only thing that I wanted you to look at was really the blue area, which is the total queue delay. Now, my question is, okay, what happens to the cycle length? What should be the cycle length that we should use? If you have like certain traffic in one direction and certain traffic in another direction, as long as you give the green times to each direction in the ratio of whatever the flow is, that's enough, right? Does cycle length matter? Something to think about. It turns out that it does matter. Okay, so if we had constant arrival flows and vehicles that stopped instantly, and accelerated instantly, the perfect case, the ideal flow, which causes the blue area in Professor Jin's notes. So this is the first term, which I said is the primary term of delay. In that case, if you just look at what happens with two different cycle lengths, all I did out here was I just took that area for one cycle length, and then just split it into two cycles. Half the cycle. Okay, you still have the same green and red ratios. I mean, it's not drawn to scale, but you still have the same green and red ratio within the cycle, but the cycle time is half. What do you see as the delay? Is it the same? How much less? It's precisely 1/4. I mean, precisely half, because you can add up the 4 of those small triangles, just turn it around geometrically, you can actually see that it's just half, right? So what that means is that if you reduce the cycle length, you will get less delay. So the Q delay is the area. Cycle length cut to half gives you the delay, total delay, and the average delay, which will both become half. So, but now the problem is that we really cannot have startup delay. I mean, you cannot assume a perfect world, right? So we actually have what's known as lost times, sometimes written as loss times, right? But I like the term lost times because lost time sounds grammatically wrong to me. So anyway, so I always write lost time, but I think maybe lost time is more commonly used. So we have lost time. So any cycle length or that we give out, that a portion of that will be lost because vehicles just waste 2-3 seconds at the beginning to get moving, and then we will normally leave a little safety clearance at the end of green times or yellow, etc. So now what happens? The lost time is fixed for any traffic stream. I mean, any movement, as long as you know the flow, you know the speed of that flow, etc. You can actually calculate what this yellow time or the lost time would be, or what yellow time you give, etc. The classic dilemma zone calculations and all of that students learn, but those are all details. We are just dealing with the imperfect aspects of traffic signal, and sort of forgetting what traffic signals do when you get into all these kind of details. So now we have lost time, but the shorter the cycle is, what happens is that once the lost time is sort of kept same, because that's for any movement, that's just the start of lost time and all that, it remains something like somewhere as little as 15 seconds for a phase, but it could be 30, 40 seconds during a cycle, depending on how many phases you have. Phases are basically the combination of movements, right? I mean, one, right turn red, and then right and left, left and straight, or whatever. I mean, left turn red, and the left and straight, and all of those are phases. And so depending on how many phases you have, you might, or intervals, and depending on the number of phases that you have, the lost time is fixed. But once the lost time is fixed, what happens is once you reduce the cycle length, the impact of the lost time becomes more and more. You agree? I mean, if you have 20-second lost time and you have 40-second cycles, then you have only half the time. But if it is 60-second cycle and again the same 20-second lost time, you have twice as much, even though the cycle length is only 1.5 times. So the effect of the lost time becomes more and more and more. If the cycle time gets close to the total lost times, the available time becomes close to 0. And now you get up to an infinity. And that gives us a classic delay figure, which I wish were available more. Why I am saying this is that, yes, you guys may remember this question, and it is a test of whether in the end, all of you who took the preliminary exam remember the important aspect of it, right? And a lot of people don't really keep in mind what this delay function looks like. And there are a few things out there. One, it is starting from infinity and falling on nearly vertically down because it's the summation of a straight line. What is a straight line? A straight line and an inverse function, right? So why is the straight line that is just kind of going up like that? Same idea, twice the cycle length, twice the delay. Remember, we said that earlier. So that's why it is just kind of tending to a line which pretty much kind of goes to the origin out there. And it, yeah.
So is this based on Webster's?
Basically,
there are also
there are the second and third term. Yeah.
So this Webster's all 3 terms.
No, this is only the first term. I'm only, all three. But the first term explains the shape of it, is all I'm saying. The first term is basically only talking about, whatever is the perfect delay in the perfect case. And there you can actually already see the shape. What in reality happens is that you'll have the second and third terms that will actually change the shape a bit. There have been recent, in fact, I know there was a paper by Nate Gardner, one of the long-time traffic theory experts, retired, and he's in Israel now. And there was a paper by them who revisited the Webster's function using a lot of simulations, which people hadn't done for a long time. I mean, people had, just been simply following what was done in the 60s and 70s. And they did a bunch of different simulations and actually showed that, that function is actually quite good. And it is close to that straight line, again, in their simulations. So I remember seeing that. But anyway, none of this really matters. It's only just to get all of you to think about what the signal control problem is. So the normal task is to pick if we're optimizing and finding the best signal time timings, we will start with that minimum point. But what will normally happen is that when you check the minimum point, there may not be enough time for pedestrians and all of that. So what you do typically is to maybe increase it slightly, and then go to 1.5 times or something. It is fairly flat is the common refrain that we always hear, which, by the way, has caused a lot of problems that some of my students have talked about around the world, because I think around the world, traffic engineers have been using significantly longer cycle times than what a delay function will show. And the reason for that is because you have all kinds of pedestrians around the world. In the US, if there are a lot of pedestrians, you will just place a pedestrian signal or something like that. But around the world, what happens is that there may be a lot of pedestrians, and you may have some of these, really wide streets, especially if you look at, places like Bangkok and Seoul and, Bombay and almost every city in China, right? You have all these wide, streets with a lot of traffic, 4, 5, 6 lanes, and then somebody is walking across, and a lot of people walking across. So it might take like 30 seconds to walk across one side. And similarly, you might have 40 seconds to walk across the other direction. So that itself adds up to, to a significant time that you need within the cycle. Now, if you're giving like a 30-second time to cross a short street, but you need like 40-second, time to cross the wider street. At what time do pedestrians cross a street? That's when they get red, right? Which means it's a green to the other direction. Think of in terms of just two directions. The wider street, pedestrians cross when the other direction has green. And if the wider direction, takes 40 seconds to cross, okay, and has typically higher flow, right? Maybe if it has twice the flow, 40 seconds to cross it, you are giving 40-second green to the other direction, right? If the other direction is getting 40-second green, then this direction should get 80 seconds. What ended up happening here is that 80 plus 40 became 120, 2 minutes. Very often you end up finding that because of small streets crossing big streets, and big streets having this problem of pedestrians, and to balance the green times and everything, they just increase the cycle length. Just keep on increasing it. That's what they do. So it's not unusual to see like 3-minute, 4-minute cycle lengths in Bangkok or Bombay or all these places. Okay, so again, because people forget that you do have a linear increase in cycle length, and the sort of the flat region is only near the minimum. After that, it is actually going linear. It is really linearly increasing. So you shouldn't go much further than the minimum. Maybe 1.5 times, 30%, something like that. But traditionally, US textbooks have always sort of underplayed this. US professors have actually underplayed this. I have notes from my own professors, which clearly say that don't worry too much about increasing the cycle length. And that has gone around the world, and it has caused problems. It may not matter in the US, but it matters around the world. Okay, I'm sidetracking there. Again, only to make you all think about what signal is. Now that all brings me back to what link-based control is. Let's go back to the perfect world in the first term of Professor Jin's notes. Okay, that's the perfect world, right? I mean the blue area with no vehicle stoppage, but in this case we also are adding no vehicle stoppage, meaning nobody is stopping. Okay, and no lost times. Let me just go back on this. Okay, what is the best cycle length for this? I have asked this question to some of the students, and to my memory, only one student has ever answered, and it was not Peng Yuan, but unfortunately. I have asked him later, and he had answered it correctly. But I had asked this person, what is the best cycle length? And based on our discussion, I know Navjot answered this question correctly in class, and he's the only one that I remember answering this question correctly. It's not rocket science, but maybe you got a pretty good idea of why that is. So it means that give as small a green as you want. Okay, that's pretty much what it means. Forgetting the pedestrians issue. Okay, so I'll come back to pedestrians at the end of the talk. That means one vehicle per green. If there is no lost time, that's what we would do. Remember, Everything was happening because remember that curve starts going up once the signal, cycle length becomes closer to lost time. If that lost time is not there, then you basically have a straight line increase. Go as small as you want, and that'll be 2 seconds. Why is it 2 seconds? Because two cars, following each other, cannot go at any better than say 1.8 seconds or so. So 1.8 seconds, is the safe car following distance for human drivers. Okay, it's not necessarily the smallest for autonomous vehicles. But that just means if you give green to one direction and green to the other direction for 2 seconds, you take up 3.6 seconds, which means the successive greens that you can give for 2 directions will be at 3.6 seconds, right? 1.8 plus 1.8, so the cycle becomes 3.6 seconds. Okay, so even though we know that 2 successive cars can go after each other every 1.8 seconds, we now need 3.6 seconds because before the next car comes in, you have to actually give a red, so the cross direction can, right? Only after the green comes up, the next vehicle can go. So it basically becomes 1.8 plus 1. Okay, you could technically make it more, 0.9 and 0.9 and make it 1.8. If you do that, you will actually find that crossing conflicts will be part of it. Okay, so to prevent it stopping at intersection, then the question is, why do we even have signals at the intersection? You thought about it? Just because the British said that in 1868, do we have to do this? In my opinion, and our opinion, and I first threw these things at Panya, and then Panya developed the thoughts with me on this. So yeah, in our opinion, why not? I mean, we don't need to have the signals at the intersection. We could just take each of the signals and move it back. Every approach has a signal and signal mass typically, right? So just move it back, say 200 feet or middle of the block, whatever. But I think something like 200 feet away would do, and just release them at certain time. What's the benefit of that?
Jay, could I ask a question?
Yeah, go ahead.
I mean, it seems to me that would work for autonomous vehicles, but I don't trust the drivers to do what they're supposed to do after you stop them. Is that an issue?
Yeah, no, that is my question to everybody, right? It is an issue. But if you had a collision warning system that basically just tells you, and a display or a dashboard display that actually says where that crossing vehicle is coming, and it basically tells you the speed at which to go, and maybe has autonomous, not autonomous, it just has got a cruise control and a speed control system that avoids collision, which is all completely possible. The technology is not a problem because Tesla has it, right? Tesla and other cars have it already because they drive by themselves. So the technology for collision avoidance is not a problem at all. It's not even that expensive anymore. In that case, yeah, I think you will get used to driving, and that only when you reach the intersection you will actually see the crossing car, just leaving just before you, and you might just watch out. But then you are doing this constantly, right, with the tail lights of the cars in front of you. Mm-hmm. And that was sort of the thinking. Anyway, I'm just throwing it there, right? The benefit in moving it back to the links is that you have you have the vehicles actually going through the conflict area without stop. If they're not, if they're not stopping at the conflict area, then you don't have all of those earlier issues. Lost times are not there. Lost times are because they have stopped and starting. So that issue goes away, right? And so if you just gate them on the links and release them, then they should be able to go through. By the way, we have modeled this, okay? this is like about a year and a half of work by Panyan has gone into this. But his results and everything, I'll just leave it for his defense down the line. But I'll just say that, this is, we have sort of seen that this is possible. But, but alas, we still have a problem. We are still using only half the time out of the 3.6. So we are still shackled by the crossing movements. We still need to make sure that we can allow people to sort of cross each other. So, Vicky was actually jumping the question already to this concern, right? What you were saying above did not really, required. I mean, we could have, even if you move the signals back, what I'm saying in the box, even if you move the signals back away from the intersection, you would still need a green and red period, was the point. And that green and red period would be 3.6 seconds. It cannot be one every 1.8 seconds. So that needs to really allow a conflict. And that's the question that Vicky was just asking. And that conflict would we want to avoid? Would we want to worry about? Yeah, at this point we are worrying about it. So we're still shackled by the crossing movement conflict. We'll see how we can get over that. Continuing on. So as the vehicles are released at intervals from mid-block, this is the beauty of the real beauty of the system, which is that, okay, at these gate locations or like on the links wherever you have the signals, the cars are kind of coming every 3 seconds or 2.2 seconds or whenever. And if they are released one after another, they go through the intersection and they reach again at a good time lag of 2 seconds, 3 seconds at the next gate location. So they may, even if they stop, it may be a quick stop of 0.2 seconds or 0.5 seconds or something like that at that stop for it to just give you, sort of like how you drive onto a freeway. That signal is already there, the RAM control signal. Yeah, it's a RAM control signal, right? It's sort of like the RAM control signal. Only difference is that RAM control signals have vehicles coming without any order. Here, these vehicles are released from link to link at a lag, right? So there is control happening all along the street. So you see no queues anywhere. That's what happens. So this is not like we moved the queues at the intersection back onto the links. No, what we did by moving the signals is that the queues that were happening at the intersection actually disappears. Just goes away. Do you see? Do you agree? Just feel free to disagree with me. If you visualize this, go ahead.
Maybe, this is a demand supply. So actually, this case, I'm teaching.
I was going to come to that. Yes.
What is the demand?
Yes. The question was, what if the demand was very high? Absolutely. If the throughput is more, there will be queue.
Yeah.
I mean, if a lot of people get onto a link from the side street, for instance, maybe there is a shopping complex and a bunch of people come out, and they will queue up at the gating location. But the difference is that this allows a throughput that is twice what we currently get. So this can actually the maximum throughput that you can get, because now you're thinking about, let me go to that. Now we are actually thinking about clearing. For the above example of 3.6 seconds, the maximum we can get is like 1,000, like once every 3.6 seconds, that is 1,000 vehicles per lane in a given movement. If they are given 3.6 second, flashing greens on the links, that's what the traffic would do, right? I mean, about 1,000. But if you look at current signals, what is the total volume per lane through an intersection? Well, in a direction, it could be 600 and 900 and all that. But the total movement is basically the the saturation flow minus all the losses and everything. That is the sum of the critical lane volume total, and that is in the design process. It starts from somewhere around 1800, 1900. Then we adjust the capacity manual down to 1600, 1400. This is per lane volume on the intersection, which is a sum of critical lane volumes during different phases. So in other words, if you have a north direction and a northbound direction and a westbound direction only, okay, only two directions, the total that you can get, only one lane, okay, it's the simplest case, one lane in the northbound direction, one lane in the westbound direction. The total that you can get for design purposes right now is maximum 1600, 1700, okay, which means it could be like 900 and 700, it could be 1200 and 400, whatever, depending on the arrival. So that's the number that you get. But you cannot go over the 1400 or to 1800 total that you get at the intersection. The scheme that we were talking about, in each direction, the north direction will get it's 1000. I mean, it's 2000. If we can do 1.8, okay. If we can do 3.6, the north direction will get 1000. The west direction will get 1000. It will go up to 2000, which is already more than, because there is no loss time. Already more. If we can reduce it, you can actually go virtually twice. In fact, simulations that Fanyan did with microscopic modeling, microscopic traffic simulation, have shown that you're going up to I think like 3200 and kind of totals, which is effectively twice what which is not surprising, because nobody is stopping, right? Nobody is stopping, and nobody is really getting any significant green time or anything like that. So the time is being simultaneously used, but then that would require us to allow traffic to flow across each other. That's the next point. Which is now think about the vehicles that are going every 3.6 seconds. 3.6 seconds, this will only give you 1000 in the north direction, 1000 in the west direction. If it's a single lane, okay? Only two movements, not the complicated case. It will only give you 1000 in this direction, 1000 in this direction per hour. Okay, that's 2000. Pretty good still. Okay, but not the 3200 that Panyan can get. For that, you have to use this idea. The idea is that now if every vehicle is leaving at a 3.6 seconds, okay, what's the distance between them? You're going to calculate for like a 30 miles per hour standard speed. It's like 160 feet. That's a lot of space between vehicles. Mm-hmm. That's like 10 car lengths. Okay, it's a lot of space for normal. I mean, 30 miles per hour is actually pretty good speed for on an average on city streets. The idea is that if we actually do the kind of things that we are talking about, we will get this 30 at least. We typically don't get 30. I mean, yesterday I read an article that that was actually listing some of the worst cities out there, and the speeds are like 5 miles per hour average. And this is the number one was a place in London, and the number two was Bangalore in India. And these numbers were basically going down to 5 miles per hour speed. But if that's because they just stopped everywhere, right? But let's go to a good speed, which is much better than what any of the cities really have on arterials. This is like going 50 miles or 60 miles distance, which is like all the way across, on arterial streets in 2 hours, which you can't do in Delhi. Okay, all right. So think about it. So it's 160 feet is like a lot of car length space. So then why don't we allow people to cut across this flow? I mean, why are we so worried about? Imagine again, westbound traffic, that's where vehicles are going every 150 feet, above, because they are gated and they just kind of send out, right? And there's this much of space. Wouldn't we just allow somebody to go across? To me, it is a no-brainer. I just don't see why we are not doing it. Do you agree or disagree? I mean, I'm just giving very simple, straight numbers. I mean, if you have this much of space between successive cars, and you are causing 1,000 vehicles to go, in one direction, and 1,000 to go in the other direction. I see no reason. I mean, just keep a signal away from the intersection and just let them cut across each other.
How would it work with like brick trucks and semi-truck for moving that where it's longer?
Yeah, then you just delay the other direction by a 0.3 seconds. No big deal. I mean, of course, detection and everything needs to be there properly for it. Either detection or they themselves reporting it to a VII system. But these, all those technology for that is available. We just need to decide to do it. That's all, right? They're not even costly technology anymore. Communication technology at least. Even you can do it over plain phones. We have a project going on right now at UCI on I think ECHO is working on this radar detection of these vehicles and just doing, and Banyan is doing the traffic smoothing of it. It's a project at Dept, the Advanced Power and Energy Program, jointly with ITS that myself. Professor Ritchie as the ITS PI, and Dr. Hyland are all involved in. And that's actually looking at setting up a real-time detection of all these vehicles, knowing the type of vehicles and doing traffic smoothing to make sure that they get to the intersection at the right time with speed advisories and things like that. So the technology is all very much there. Okay, so it's not it's not anything that we cannot do. So if we are releasing them every 1.8 second, we are saying that we no longer have cycles. Both directions, from one direction, okay, one vehicle leaves every 1.8 second, maybe at a 0.9 second lag, the other direction is released. So they kind of go across each other in the middle of the gap, right? You can imagine this, right? Imagine a westbound direction that has a signal that is basically releasing it every 1.8 second. And then the other direction releases it at 1.8 second, and they leave a gap of, say, 0.9 second between them as they go into the intersection, which is like the 160 feet. When two cars are going like that, middle of it, this thing, that game that you play, you go like this and you put a hand in between, right? It's like that. I mean, you have like cars going, after another car just go through. No big deal. Okay. Oh, those are his PhD work. Okay. Yeah, If we stop worrying about causing traffic, we can finally shake off the shackles of traffic. That's basically my theme today. Okay, that is the theme. If you just go ahead.
Yeah. So I think this comes with a lot of assumptions on the accuracy of positioning, the detection system, and it works because it's built on the reliability of one system.
Yeah.
And I think this gets to also the arguments or counter arguments for autonomous vehicles. Generally, we want to achieve a kind of safety rate of 10 to -6, something like that. So since if we have so many systems, rely on so many systems, and if one fails a certain rate and this multiply together, will this lead to substantially higher failure rate or accident rate than current system, which definitely is not the most efficient. Because we define signal, we always this trade-off between safety and efficiency. So, is there a way to measure potential safety or to come to
Yeah.
take care of this edge case?
Yeah, that is great question again for those at the Zoom. Professor Jin's question was, this would require multiple systems being put in place. One the signal part is standard, but at least in terms of detection and and then collision avoidance systems, which may be on individual vehicles. I mean, how do you know? I mean, if somebody has a car where the collision avoidance system is faulty, okay, all these are possible. So so is there like possibilities of sort of cascading failures and all of those kind of issues needs to be modeled, but we have done the initial safety work, and then that's the next set of slides. I'm just going to that. Yeah. So the question really, I think that question brought home the real issue, which is, okay, we just need to make sure that it's safe. If it is safe, let's do it, right? I mean, I see no reason why. And remember that we are actually talking about doubling the throughput of our streets. I'm okay if it only goes up 50%. Right? One other thing to remember is that the one thing that the demand supply interaction causes, again, Professor Jin touched on this earlier when he was commenting. One thing that the demand supply interaction causes is that if you don't have throughput, these vehicles will sit in the network. They'll have to sit in the network. They have to sit in the network, and they cause congestion, and they'll cause the queues. But if the vehicles are getting in and getting out faster, then that by itself helps. So if you increase the throughput, in this case, that reduces the delay. Okay, like we said, we can imagine why they may not stop anywhere. It just kind of come to each of these link places, like entering a freeway, maybe just stop for like a second or something, or slow down, and they don't even have to really stop. I mean, no big damage if they just kind of slow down and continue expecting the green. And it could be an onboard display that basically becomes red or green as they move along the link to, by the way. Yeah, this is also possible. A continuous green, which we are not studying, but it could be very interesting. A continuous red-green spectrum as they are driving. Anyway, back to the question: if people are actually clearing and we are getting that much of extra throughput, then people will leave the system faster. They'll be moving faster, and everything is much better. So increasing the throughput will reduce the delay, and reducing the delay will reduce the number of people who are going through, who are in the system at any given time. So it reduces the density, which helps increase the speeds, right? So there is all these back and forth interactions. Crossing conflicts. I mean, we already talked about this, but I mean, I was throwing this in case you guys weren't already scared. But Vicky already said that she was scared, right? So I guess I did my part in scaring everybody by now. So crossing conflicts, my God, we are dead. Okay.
Jay, something to add in. I just from a human, behavior perspective, I'm not only scared of the other drivers, I'm scared of me. I mean, I'm not confident that I could follow the instructions.
I'm scared of only me. Go ahead. Yes, you're right. Yeah, it is both. So I mean, really, the technology needs to be there. The collision avoidance technology needs to be there. I mean, I wouldn't suggest putting this out there, but what I know is that for the numbers that we are seeing and the gaps that are available, I don't think technology is a big. I mean, we are not talking about just sending two cars right behind each other, so they could hit. We are actually talking about some time, I mean, some distance between these vehicles, right? Yeah, I mean, that's what that 160 feet that I was talking about. We're talking about some distance between them. So, I mean, this does not need, I mean, let me go to collision avoidance systems. If you consider aircrafts, they have collision avoidance systems. They need to be extremely, accurate and fail safe, because they in 0.1 second or 0.005 second, you could have something go completely wrong, and two aircrafts could just close in so much. But we are not talking about a system that's that highly dynamic or anything. Despite what we like to think, our traffic systems are actually fairly mild, systems in terms of control and safety, if we want to think about it. Okay, that's why the Teslas and the industry figured that we have the technology for this, and they went for it, and they found that we have the technology, and the Teslas are driving on the road with the driver sleeping inside, right? Nothing happens. So the technology is very much there, but I think Vicky was talking about a different aspect, just the plain fear that people have, and I understand. So that will go away only when we know that this is running fine, and we need to sit in a car a couple of. I haven't sat on a Tesla. I don't know if have any of you driven a autonomous Tesla driving by itself. You have? How does it feel?
It's kind of Tesla.
Volvo, okay.
It feels almost like somebody else is has a helping hand, except for when it doesn't work.
When it doesn't work, yeah.
So it's perfect. I-5 freeway, straight off.
Yeah. Well,
The second it has a problem, you're like,
oh, you guys get, yeah. I haven't been on one of these, actual autonomous vehicles, trying to drive or 100%, level 5 autonomous or whatever. I haven't been on one of those, but I assume that I will probably be scared, at least for some time, till till I know that, okay, this is working well. Only very few deaths so far from these autonomous vehicles. There have been, but very few. Okay, so it will take a little time for us to get used to it. But once we know that, it is working, and then it should be okay. Is my sense. So just continuing, how serious is the accident probability? So we do have to study this. Well, okay. I will try to finish soon. How serious is the accident probability? Can we look at the probability in terms of the chances for one vehicle space-time trajectory? That is, what time any vehicle is at what point in space, 2D space. So if you can just imagine flat, flat surface and 2D space with a time axis. So where the vehicles would be. So that's like a time-space, trajectory in 3D. If the chance is essentially the overlap volume, okay, that's what we will actually see is that I'll show some figures. So if you have a car and it's just moving over time, it's basically it's a car here in space, but if that's the time axis, right? It is just kind of moving like this, right? So you basically have a tube. That's what happens. So different cars are tubes in time space. Our only issue is the chance for a collision is if these tubes overlap, right? Where a car is at what time overlaps with where another car is at that time. So we can actually see the probability is almost the overlap volume. Okay, the probability for an accident. Yeah. Go ahead.
Would you consider the tube in the sense have solid edges, or would it be a gradient of the chances of cars?
The first analysis that Panyan did on this had it as a fixed edge. So the tube has a fixed cross section dimension. The second was actually a stochastic version where there is a probability distribution that what we think should be the speed or what is recommended to it or what the machine does.
So we now have two versions and combined together. And if the solids tube cross, then definitely like the probability is 100%. manage like with the like speed distribution, so that they have some probabilities, but not all.
So yeah, in the simulated work, of course, we haven't done anything in the field, right? So this is all computer modeling only. So in the simulated case, yeah, we are applying a little distribution of it to see what will happen. Such, they are recommended, when the signal shows a certain green time, which may be a flash of green, okay, and the car goes, we expect the car to be at the signal at a certain time. If we apply a little error to it, or perturb that stochastically, we can actually see what's the chance for it to get close to the crossing vehicle. Okay. Again, this is only a chance for an accident, but it does not address, again, what Professor Jin said earlier, not its severity. Severity really depends on what type of, at what angle these two things crossed, and whether it was a front end hitting a back end, or it's a front end hitting a front end in terms of the velocity vectors and the resultant vector of the movement. It's a plain physical problem. I mean, you can write the equations with trigonometry and add a little variance over it, and Penguin has done most of those things already. Then the problem is for us to know severity in terms of the type of collision, right? How many, whether people would die. It just depends on the characteristics of the car. There isn't enough data on some of these kind of things. Okay, but it is, we could study there is a probability distribution of movement. So your question was my next item of movements away from the perfect trajectory. So we can actually find whether, we'll find that car following. So this is where it gets very interesting. If you actually look at the chance for a probability, rear end collisions are highly probable. You know why? Because we are constantly following. And so if you think about the probability for an accident at a point in time, that there are too many points in time where it can happen. But you think about a crossing conflict, that only happens in a split second. That's it. One decision by the driver to hit a brake will do to avoid it. But if you are driving behind each other, this accident is all along the way. And we have been avoiding, that accident all along. So much of brain usage has already been there in avoiding accidents. And I think we can do this with technology assistance at collisions. So that's where this vehicle tubes model that we explained just now was. I'll show some pictures from Peggy next. So this was a paper that Penguin presented at TRB this time. And so it's the same idea that we were just talking about. So from one intersection at a different time, T1 to T2, the vehicle would have moved forward. So it forms that tube, from one place to another. And these are some tubes from his modeling, just something that I just pulled out from a bunch of things that he had sent me on it. So you can see the car following version. The two tubes are just kind of behind each other. So if you perturb either of them, by any amount, they overlap constantly. The first one at the top left. Whereas like a merging, diverging, this actually is a left turn movement or a right turn movement and a straight movement. So depending on whether you're in UK or in the US, this could be actually diverging movement or merging movement, I think. The third one is actually a conflict movement, a left turn conflict with a straight movement. Okay. Again, you can see that in the bottom one, that crossover really only happens at one point. So you don't have too much of accident probability volume there. Whereas the other cases may have more, and numbers that Penguin pulled out actually showed that there is a lot more probability. Yeah. Go ahead. I think you tried three different models, right? Four
models
different.
are all tested.
Which
Like the new
Chips,
Newell's,
Newell's,
yeah, Chips, Newell's, OV,
yeah.
and
Did you-
intelligent.
Yeah, intelligent driver.
Which is well known actually in fact, I mean, some models are totally just
So-
collision, 100%.
Oh, yeah, because the model itself avoids collision, right? Yeah.
Like General Motors. Model.
Yeah.
I'm glad that you did not use General
Yeah, no, we didn't use
Motors.
General.
We use General Motors 100%.
Because GM will just keep on hitting, right? The cars will keep hitting each other. Yeah.
Many other also matters a lot. So actually, that is something very interesting. But I think in the real world, people are more intelligent than these models describe.
Absolutely, yeah. That's why they don't hit each other. So this is basically probability calculated in terms of a blind volume of overlap. The point that I was saying was that in the real world, drivers actually constantly, intelligently adjust their speeds and all that. But the one point out there really is that it is not really much of a driver overload to avoid that small volume, high severity collision that could happen at an intersection if we have technology. That basically actually displays on the, imagine you're driving on a car and you have a display on your dashboard that basically just shows a crossing car just kind of coming to the intersection. You can see this. You can see this, right? And then you're driving up to the intersection, you will just slow down. Okay, that car is coming. I'm just going to slow down. And then the car goes, you accelerate and you pick up speed and you get to the next gating location. So I don't think this is too difficult. That is basically the conclusions that we are getting to. So that's the next question. Are crossing conflicts so terrifying? As we found from the simulations that no, it's car following is about as bad. But crossing conflict entails much less overlap volume. Minor adjustments, in my opinion, only minor adjustments are. But this has to be tested, right? I'm not going to put this out there in the field till we actually do some pilot, pilot checking of it. But human drivers, we believe that they can certainly do this. Collision warning systems exist. I described all of this earlier. I'm just summarizing it. Onboard devices, showing crossing vehicle positions can help. It's a no-brainer for autonomous vehicles. If you have autonomous vehicles, we should have no signals. We should just completely take away any idea of giving green and red signals. But if you look at the literature, there are a lot of papers that are actually trying to kludge signals, the current signal schemes for autonomous vehicles and to make adjustments. No, this is not a question of adjustment. If you have autonomous vehicles, zero signals. There should be no signals. There's just no reason for signals. Okay, that's what I meant by it's a no-brainer for it. This is the part that I was mentioning earlier, that the vehicle tube model that we have now, again, is making some changes in looking for sort of the accident models or the severity models, which are, I guess, very poor in the literature, sort of. So I don't know how far we will get with that, but we'll try. We'll try. This is all the case, then let's go for link-based control. That was the theme. Intersection signals must go away. Freedom. We have got rid of, yes, yeah, got rid of our shackles. Speaking like a political leader. Okay, ordered movements. So now comes details. And I don't want to get into the math of these details. What happens if you have multiple lanes? Because multiple lanes, vehicles are, enter in the intersection at different times. They can, because the collision may be happening like 30 feet differently, because it's with the fourth lane and the first lane here. You understand what I'm saying? If you have north direction, you have like 3-4 lanes, and a west direction has 3-4 lanes, and there are those extra 10 feet and 20 feet, and all of those things matter, because we are talking about a gap. So there needs to be some sort of ordering of these gaps I know Pena sent me a simulation of this and don't have time to show that. But there is like a 2-second time gap. Actually, let me show you a video. Should be okay, right? If I just simply stop sharing and go to a video file. So let me stop sharing. Screen sharing has stopped because external display is disconnected. Is that a problem? Hopefully not.
I think it's fine.
It's fine. Okay. So where is it? I'm gonna yeah. I'm gonna stop soon. Yeah. And I don't have much more. So I'll just show 2-3 videos, and I think I've given enough of an. Oh yeah, you can see it. Yeah. Okay. So yeah. Yeah. So I'm gonna share this again. Should be this. Yeah, there's some minor sound. Can you see this, Vicky?
Yes, thank you.
Yes.
Oh, okay. So yeah, Pena thinks that there are only Toyotas and Teslas in the world. So that was one version of it. I'm going to stop share and share another version, which is probably also interesting. Where is it? Just show it. A 0.2-second version. I will share it. Okay. Okay. I'll have to share screen again. Share. Yeah. These are basically different cases where you can actually see that the vehicles are lagged from lane to lane and all of that. So there is some lag from lane to lane, and it actually ends up giving you an interesting mathematical optimization problem in design, where you need to actually create a matrix from each lane for a movement to a certain another lane and stuff like that. It's interesting problems, but the numbers on them aren't there yet, so I won't go there. Let me just go back to sharing the talk itself. Share screen. Back to. Oh, I need to maybe make it. Hold on. Go to screen. Okay. Now I should share again, right? Yeah. Okay. And I should share. How do I go to share? What's that? And? Oh, yeah. Okay. I just wanted to get the zoom. Yeah. Okay. And but I'm not seeing the full screen, the second screen that Jared showed me earlier. Jared, can you see it? There should be a second screen, right? Or is it not in? We'll be back in 5 seconds. Oops. Oh, the Z button is not working.
It's not working.
Yeah. Oh, yeah. This laptop is just kind of falling apart. I need to get another one. All right. We lose it. I can actually just go to the other version without the full screen. I guess. Oh, it's okay.
Yeah. we can see it.
Oh, it's fine. Okay, I'm back. I only have very little after this. So this idea of multiple lanes is simply a matter of lagging them. You can imagine, like for a simple case, northbound, eastbound, westbound, southbound, you can actually make it in an order by lagging them like 0.5 seconds each. And then you need to lag when you have multiple lanes by say 0.1 second and things like that. Okay, that make like the tail of one car just go past and then another one in front of it, another one, behind it, another lane, and then each of these cars will come at a lag to the intersection and go through very nicely. And those simulations are very interesting. So it basically gets to a matrix optimization problem, which was part of. So I've left it as a some forthcoming in a paper. It's done, but it's not. So simulations have established the feasibility of it. This is just to show that Peng-Yuan has done a bunch of things. I needed to show a few of his slides, right? So these are all Peng-Yuan's formulations of variables and a lot of nice car pictures. He has a ton of these slides. Oh, and there was another thing which I did not mention, which was a speed advisory smoothing control that actually happens as the vehicles get to that point. You can kind of see that as the vehicle moves, their speed has to be kind of told to them at what speed they should go and all of that, which may not be necessary in all application cases. But so there's an optimization of maximizing the traffic efficiency in terms of the time of. This is a throughput optimization, by the way. Again, okay, not a minimum delay optimization. It's a throughput optimization. So clear the traffic as quickly as you can is the point. Okay. This is all these movement vector matrix formulations that I was mentioning earlier. Don't have to pay attention to the details. Just know that Peng-Yuan has done all this. A bunch of constraints on it. Okay, finally, this is my final slide. What do you do about pedestrians now? Earlier, I was kind of saying that pedestrians are a big issue, and then I kind of, if we have all these cars going around with no signals out there, what do we do about pedestrians? Red phases were always the time for pedestrians to walk. So that's no longer there. So I mean, we just simply stop the system and make people queue up on the links every now and then, okay, for a little time. So if we for instance give a 30-second pedestrian, now you remember one benefit is that you don't need pedestrian time separately for different things. This 30 seconds can be when everybody just walks across everywhere. They don't have to cross northbound and then westbound. They can just go diagonally across the like those Japanese pedestrian control things, right? I mean, this kind of walk across, and they can do all of that, but that's for 30 seconds when all these other directions are basically stopped. So if we do that for every once every 4 minutes or so, that we could still get pretty high throughput. Instead of getting 2,000 per direction, maybe 1,800. 10% of the time is lost. But then wouldn't people have to stop for like 3-4 minutes at an intersection to wait there before crossing? Turns out that that's not needed either, because now you can actually coordinate the 30 seconds for pedestrians. Now you no longer have signal coordination. You don't need any signal coordination for the traffic. The signal coordination is for the pedestrian signals. So imagine, not 5 seconds, I meant 5 minutes, okay? Not 5 seconds. That was a typo there. We'll have to wait for 5 minutes. No, they don't, They could actually, imagine a block to block is 1,000 feet distance. That'll take 5 minutes. So if you are giving a green here, give a green after 5 minutes at the next block for 30 seconds. So if you're walking along a street, you'll keep getting your green tops. So you can use the offset schemes. So I call it offset within within codes. So the offset schemes used for traffic will then be used for pedestrians. So we'll basically end up with a system where the traffic controls will be for pedestrians. Ultimately, human drivers will stop driving and will be all autonomous cars. But that will probably take 30 years or 25 years. The system that we're talking about is applicable as long as pollution warning technology is there and it's all put in place. Human drivers can do this with technology assistance, you could say. But once you have fully autonomous vehicles in another 20, 30 years, whatever, we will need to set only pedestrian signals. That's all I have, on a very open-ended seminar where, it was just raising some of these points, and thank you. And that's all I have. I'll be glad to take questions.
Let's thank Dr. J for let's give Dr. J a warm applause. Thank Dr. J for their time giving us a seminar. And I was wondering,
other questions that I could answer. I did not look at the online questions.
Yeah,
There are some questions on chat box.
yeah. I was wondering to give Dr. J a thank you note.
Oh.
This is from the ITSDSA. Thank you for.
Well, all of you being here is the thanks, right? I mean, this was really a presentation for our purpose also, I was just throwing it out there. I mean, even though I sounded very confident that this is all correct, I don't know. You guys, think about it. And if you find issues, let us know before we sign Pangyuan's dissertation. Right. So this was actually, I should thank all of you for listening to it, I would say, So thank you for the thank you note.
I also want to thank the audience from the online, especially Lindsay. She's currently at 4 a.m. in the morning.
Oh my God.
And thank you for
Sorry to
staying
keep
so
you.
long.
Yes.
Oh, and she's still there.
She's still there. Oh,
Hi.
it's nice to have you.
Yeah.
And look how awake and alert she looks.
Yes.
I look forward to seeing all of you, including the audience online next time. And next week, we will have a seminar by Professor Ram Pandiala
Yes.
from ASU. He will be visiting us for a full day visit. Maybe there is a breakfast with students. Please sign up. And his seminar will be from 11:30 to 12. Or 12:30.
Yeah. We have some questions on that.
Yeah. You want to read the questions?
Yeah.
Or maybe I can check.
Yeah.
I can stop share.
Any questions from the in-person audience? Professor Mary?
Yeah. My God, Mike has a question. Mike McNally.
I didn't have a question. I just made several comments in the chat along the
Oh,
way. So they're
Mike,
kind
do anything that I can answer quickly?
of,
Otherwise, I'll take your comments to heart. And
I made a
take
whole
them.
bunch of them. In there. I'm not sure which ones are most relevant looking at them. In your discussion on severity of potential accidents, I don't recall if you mentioned speed, because clearly at a residential intersection, when cars might be going 30, it's quite different than a major intersection where cars are going 55, 60. I don't know if you introduced speed into your
Yes. All of the simulations that we have done have speed as a primary parameter. So we have looked at the different cases at different speeds. So
I meant relative to policy. Is there a place when a higher speed negates what you're proposing?
No, if they are at higher speeds, there will actually be more distance between them. Typically,
Theoretically,
theoretically, they can
not
be
going into a signal. I don't think you may see that.
No. I mean, if it is
a freeway.
Yes, I mean the idea is that this will no longer be as much of a congestion related speed. This is really a control speed that we actually set.
And it probably wouldn't be distance between the cars at that speed. It would be the time between cars at that speed.
Yes, but distance and the time
The
time
distance
may
is
remain the
irrelevant.
same.
It's the time it takes for a car to go between two vehicles that don't need
That's right.
to slow
So
down.
if you're releasing vehicles at the same sort of time interval or similar time interval, Penguin has some calculations on it. But if you're releasing them, if they are at a higher speed, then they basically will be creating a bigger distance between them, which actually says that the crossing conflict actually happens within the same 1.8 seconds, right? But now the cars are going faster, but they are farther. See, does that make sense?
Okay, no, because I'm looking at distance being the appropriate variable. Farther apart of the higher speed might actually be closer together.
Yes, yes. In time space, the time space distance, I think they would come somewhat similar, but there is significant influence
But a
of the
vehicle
speeds, as you
crossing has
said.
a fixed distance to cover. The
Mhm.
time that the gap is what's critical.
Yes, time gap is critical. Yeah.
Another comment I made, just in case someone else missed it in
Very
there.
quickly, the distance is important for the people who are sitting inside, right? For them to feel safe. If there is sufficient distance, then even at a higher speed, they'll be okay.
Well, that's a perfect lead into my other comment, and I'm not sure if everyone saw it or not, but over 100 cars run into fixed storefronts every day in the United States. Over 1.1 hit a 7-Eleven every day in the United States.
Over 100 cars do what? 100?
That cars, over 100 a day of all storefronts, 1.1 7-Elevens alone per day.
Yes.
So you want those drivers out there?
I mean, true, but the other side of the equation is that when you actually look at how much time people waste around the world on traffic signals, I did a calculation, and this was only for South Korea, and I ended up with numbers like they may be losing 1% of GDP on just sitting there. It could be 1 to 2% of GDP sitting there.
Wait, what's the opportunity cost? What would they be doing if they weren't wasting time at the signal?
I was just, David is not here to ask about the economics of it, but I was just simply using placing a time value of something like $40 or $50 per hour. That's it.
Okay, value time's another argument altogether, but I tend to think that people sitting in a queue almost anywhere, but a traffic queue at a movie theater, whatever else, are the least likely to do something stupid or dangerous. So why not just let people sit in queues all the time?
No.
I'm not being funny, by the way.
Well, that's
the last time you were in the queue and someone did something evil.
Yes. I mean, all of this, I guess we will have to discuss, because I'm actually talking about throwing signals on here, right? So
these are the definition of civilization.
Yeah.
You're waiting in line, you're part of civilization, you're not going to hurt anybody.
Yeah, we'll see. Any other question that, thank you, Mike. Any other question that I should answer? Let me just check. Vicky was saying a driver-facing dash cam might be revealing as to how terrifying it really is. That's a great point. We may be able to. I mean, we may even have systems, right, that could actually measure their reactions and appropriately guide them. It's like somebody just goes like that. It's like, okay, calm down. You are allowed to stop at the signal, for the next, 30 seconds. We will turn the signal on once you are ready to go. Right? Maybe we need to do that. So anyway, okay. Anything else?